Okay, so yesterday we did properties of rational exponents. So the properties of fraction exponents. And what you should have realized yesterday, I said it at the very beginning, is those are the same properties of exponents from Algebra 1. I didn't teach you really anything new yesterday. You already knew when to add exponents, when to subtract exponents, when to multiply exponents, that anything raised to 0 is 1, and that negative exponents should turn into reciprocals for the base, or flip what they touch. And today we're going to focus on the properties of the radicals. So these would be properties of square roots, cube roots, fourth roots, fifth roots. Like all the problems I assigned to you last night looked like fraction exponents, but maybe you looked around at some of the other problems and they look like radicals. Now, one thing that we kind of need to be aware of is, if let's say something looks like a rational exponent and it doesn't follow the properties of exponents, then maybe you should try changing it into radicals and see if you can do anything in radical properties. Because they're essentially the same thing, right? A fraction exponent is a radical. Okay. So you can go in and out of either form, and then depending on which form you're in, you might be able to select a property. Okay, so we have a product and quotient property of radicals. So that means that we are multiplying or dividing radicals. And because we're talking about all the roots, square roots, cube roots, fourth roots, etc., you're going to see me use the nth root here. Okay. The multiplication property of radicals says this. Suppose you have the nth root of a, and you're multiplying it by the nth root of b. So notice in these radicals, the index or the root is the same. The radicand, remember that, the stuff underneath the radical, may be the same, may be different. Okay. So you have to have the same root. If you have the same root, so I'm multiplying 2 square roots or 2 cube roots or 2 fourth roots, then I can multiply the radicands under one root. It stays the nth root. And division is similar. Suppose you have the nth root of a divided by the nth root of b. Okay. The root is the same, the index. Okay, so they're both cube roots or they're both fifth roots. A and B may or may not be the same thing. Usually it's not the same thing if we're going to use the properties of radicals. But the division or quotient property of radicals says, well, you can make that one big nth root and just do A divided by B underneath. Okay. So a couple of things you might write off to the side that would be helpful. Must be the same root. And remember, that's, if you go back to section 5.1, that's the index. It's the number outside of the radical. And it must be the same root. And, side note, this property will work both ways. So if I have two separate radicals that are being multiplied, I can put them underneath one radical. Or if I have one radical with lots of things being multiplied underneath, I could separate them out. Okay. We essentially, or I use this first property when I'm doing simplifying radicals, like the square root of 12. We don't know the square root of 12 exactly. So I turn 12 into a product. I look for a factor of 12 that is a perfect square, 4. I turn 12 into the product of 4 times 3, which that's the same thing, right? And then essentially I'm using this property that says if I have the nth root of a times b underneath, I can separate it out and do the nth root of a times the nth root of b. So I'm doing the square root of 4 times the square root of 3, and the square root of 4 is 2. So all along, and we've been doing this since early on in this semester, all along we've been using that property of radical. Right? And these are already things that you have done in Algebra 1. Okay, so let's look at some of the examples. Okay. If I came across something like A, I would first check, like, can I do a cube root of 2? No. Can I do a cube root of 4? No. So let me see if I have 2 cube roots that are being multiplied together with the same root. Keep it a cube root. Do 2 times 4 underneath. That's the cube root of 8. Well, that works out nicely. Cube root of 8 is 2. So sometimes when they're two separate radicals, you can't evaluate them. Like, we don't know the cube root of 2, we don't know the cube root of 4. But when we put them together, we do know the cube root of 8. Okay. Here's one with letters instead of numbers. So this one, I usually don't, like, I can actually simplify this one, the cube root of x to the 4th right now. Okay, but what I think is, like, okay, I could simplify it and then multiply it, but then I might have to simplify it again. So, like, ideally, if you see that you're doing cube roots of things with the same base, I would combine them first and simplify once. So we can say this is the cube root of the 2 radicands, which are different, x squared times x to the 4th. Well, I should add my exponent. That's the cube root of x to the 6th. Do you know the cube root of x to the 6th? What multiplies by itself 3 times to give you x to the 6th? Wouldn't be x, right? Because x times x times x is only x cubed. So maybe try x squared times x squared times x squared. What do you do with all your exponents? Add them. You'd get x to the 6, wouldn't you? Or think about it like this. If you have the cube root of x to the 6, this root belongs where in the fraction exponent? In the denominator. So if I rewrite that as a rational exponent, that's x to the 6 over 3. Which is x squared. I don't usually rewrite it, I just like think about it, but I mean that's another way for you to do that. You can turn it into the rational exponent. Okay. So it comes out nicely. Okay, letter C, 4th root of 240 divided by 4th root of 15. If you check your 4th column on your perfect squares, cubes, fourths chart in your notes, those aren't on it, right? So we'd either use our calculator or attempt a property of radicals. Since they're both 4th roots, I can keep the 4th root, and underneath I can do 240 divided by 15.
16.
That is 16. So the 4th root of 16 is 2. Now, if I had written that the other way, the 4th root of 15 divided by the 4th root of 240, then when I rewrite it, I would be doing like 15 over 240, which, you know, that reduces to 1 over 16. So this would be an example where I had 2 4th roots that were separate. I used the quotient property to put them together. Okay. I simplified the quotient 15 over 240 to get 1 over 16. And then to actually evaluate the 4th root of 1 over 16, I could think about like basically breaking it back up. So the quotient property would say like these two things underneath together can be the 4th root of 1 separately over the 4th root of 16. And are those things you can evaluate? Yeah, 4th root of 1 is 1 and the 4th root of 16 is 2. I mean, it would just be the reciprocal. That's all I did was flip them. Okay. But that's an example where, like, sometimes you use the property to put them together, and then essentially you're breaking them back up to evaluate it, okay, in a fraction form. Okay, D and E on there. This is what I was kind of like alluding to earlier. Notice that D and E look more like our problems from yesterday, right? They have fraction exponents. So if I initially saw D, I would think about, oh, properties of exponents. Should I add the exponents, multiply the exponents, subtract the exponents? But then I look at D a little bit more carefully, and a big difference between those two powers is that they have different bases. So I can't use my properties of rational exponents. So I might be like, well, there's nothing I can do. But what if you could? Okay. Since they're both being raised to the 1/4, they're both 4th roots. This is the 4th root of 3 times the 4th root of 4. If I have two roots that have the same index, I can combine them under one root. That's going to be the 4th root of 12. And I might check to see if I could evaluate or simplify the 4th root of 12, but I cannot. So okay. But I can group them together. You know, when you look at it in rational exponent form, essentially now when they have different bases and the same exponents, they have the same roots right there, you're multiplying the bases and keeping the root. Okay, that's the property of radicals. Okay, so similarly for 12 to the 1/2 and 3 to the 1/2. So they're both being raised to the 1/2. They are both square roots. Square root of 12 over square root of 3. You might, if you decide there's no property available to you because they have different bases and rational exponents, you might change it to a radical and see, is there anything I can do with properties of radicals before I give up? Right? So you can change in and out of the two forms. That's really the square root of 12 divided by 3, which is 4. And then, of course, the square root of 4 is 2. All right, any questions about multiplying, dividing? Okay, now note, that does not work for addition and subtraction, right? We only did that property for multiplication and division. So adding and subtracting radicals is something different. Okay. Here's what you need to know about adding and subtracting radicals. When you are adding and subtracting radicals, you're essentially adding like terms. Okay. When we talk about like terms in radicals, it's got to have the same index, so the same root. And the same radicand, the stuff underneath the square root. Like, they have to be exactly alike. Roots and numbers or values underneath the radical. That's the only way you can add them. I always tell like a stupid story. Here it is. Suppose there was a Sam's Club for radicals. Okay? And you could go into the Sam's Club and there were just aisles and aisles of radicals. And you're like walking with your cart and you're like, oh, hey, cube roots of 2. I needed some of those. So you put 2 cube roots of 2 into your cart. And you start moving along, but you're like, you know what? I can never have enough cube roots of 2. So you back up a little bit, and you put 3 more cube roots of 2 into your cart. How many cube roots of 2 are you taking to the checkout? 5, if you were listening to my silly story, right? You put 2 in, then you went back and you got 3 more. You have 5 cube roots of 2. They do not turn into cube roots of 4 or 6 roots of 2 or anything like that. We don't change index, we don't change radicand. They are just objects on the shelves. And we are just counting how many of those things we have. And they have to be exactly alike. If I put a cube root of 2 into my calculator and then I go find a 5th root of x, that's something totally different. They may have different prices at checkout. So they're just things. They're objects that you're adding together. So let's see. A, how many cube roots of 3 do you have? 3. They do not become cube roots of 6, cube roots of 9, 6 roots of 3, anything like that. Don't mess with the index. Don't mess with the radical. I had 2 cube roots of 3 plus 1 cube root of 3. That makes 3 cube roots of 3. I'm adding the coefficients. 7 square root of x minus 3 square root of x. I have 4 square roots of x. Maybe I was walking down the aisle, I put 7 square roots of x into my cart, and I thought, you're getting a little bit ridiculous, Ms. Cronk. You put 3 of those back. So now I only have 4 in the cart. Okay. C. 6x to the 2/3 plus 5x to the 2/3. I have 11x to the 2/3. That one shouldn't be such a stretch, like in terms of like leaving it as a rational exponent, because it's just like when you guys are like maybe like foiling stuff out, don't you add the like terms like x's go with other x's, so you add them together. So x to the 2/3 just adds with other x to the 2/3, but it wouldn't add with an x to the 5/3 because that's a different term. Okay. And then D, cube root of 40 plus cube root of 5. Can I add those as is? No, they're not like terms, right? Like essentially in my story, a cube root of 40 is something totally different than a cube root of 5. Okay. Before you leave a problem like this, make sure all your radicals are simplified. Okay. So we haven't really ever simplified a cube root before. This one's going to be a little bit new. Okay. It's just like when I was doing that square root of 12 earlier, and I said, okay, I'm going to look for perfect square factor, 4 times 3. So I got 2 square root of 3. Since this is since this is a cube root, we're looking at 40. Do you have any factors of 40 that are perfect cubes? So think about your perfect cube list, or look at your perfect cube list. Any factors of 40 that are perfect cubes? 8. 8 times 5, right? So this cube root of 40 is really the cube root of 8 times 5. Okay, they're the same thing. And then using my product property for radicals, this is the cube root of 8 times the cube root of 5. And the cube root of 8 is 2. So this is really saying 2 cube roots of 5 plus a cube root of 5. And now I'm at 3 cube roots of 5. Because this one doesn't have a leading coefficient or like a coefficient in front of it, it must have a 1. So there's 3 cube roots of 5. So like, don't always give up right away. You might still be able to add them, but there could be problems where like you can't add. So like an extra example, if I had a square root of 2 plus a cube root of 2, can't add those by radicals because they're not like terms. If I change them to rational exponents, 2 to the 1/2 plus 2 to the 1/3, I don't have a property for adding powers. I have properties for multiplying powers and dividing powers and raising a power to a power. There's nothing I can do. That's as good as that one would get. All right, any questions so far? Yes, Alex.
Well, with that, couldn't you just make the 1/2 into 3/6 and make the 1/3 2/6?
If they were being multiplied, sure. and then you would add your exponents, right? But that's if you flip back to the other side, that's the product of powers property. This is a sum of powers, right? A power is a base and an exponent, a base and an exponent. And the operation between them is asking you to add them. We don't have a property for sum of powers, so there is nothing to do. And that's where it gets like a little bit confusing because you're just thinking like, I have to do something, right? Well, you have to make sure that you're following the rules, so you have to think about those properties. And that one is very easy to confuse. Good. Does that help answer your question? All right, we got 2 more things to talk about. This part might be new to you, okay? I think the other stuff, like, you should have done before, like trying to combine, like, terms or trying to separate or put together radicals. This part is, I had mentioned, like, for that cube root of x to the 4th that I really could have simplified it, but since it was being multiplied, I would multiply first and simplify once. So here's where, like, we want to simplify with variables underneath. Okay. If you stop and think about the cube root of x to the 5th, you might say, well, is it x? X times x times x. That would be x cubed, right? If it was x squared times x squared times x squared, add up all those exponents, that's x to the 6th. So x to the 5th is somewhere in between, meaning it doesn't have a perfect cube root. Okay? What you want to do for a problem like this is break up this x to the 5th so that it is a perfect cube. So x to the 6th is too big, right? We don't have that. We only have x to the 5th. We're going to break this up and say this is the cube root of x cubed times x squared. You agree that that says the same thing, cube root of x to the 5th? Okay. And then think about your property of radicals for products. You're allowed to do the cube root of x cubed times the cube root of x squared. You're allowed to break it up because it's being multiplied underneath. That's allowed. Multiplication and division. And then what's the cube root of x cubed? X. Times the cube root of x squared. That's fine. There it is. All right, let's look at B. Okay, what I would maybe think about for B when we're like starting out is it's kind of like that one we asked about here, 63. There's like lots of different things under the radical, right? So take them one at a time. Like, can you do the 4th root of 256? And then can you do the 4th root of x to the 6th? And then can you do the 4th root of y to the 7th? Well, can you do the 4th root of 256? Is that on your list? Yeah, 4th root of 256 is 4. Okay, the 4th root of 6, the 4th root of x to the 6th. I can tell it's not a perfect root because if I think about changing this into a fraction exponent, my root is 4, so that would be my denominator. It would be like 6/4, and that's 3/2, and that doesn't divide nicely. So I can do like I did over here, okay? What's the lowest multiple of 4 that is like under 6? X to the 4th. So I could rewrite that as x to the 4th x squared. And then do the one that you can do the 4th root of nicely. So the 4th root of x to the 4th is x. That's going to come out with this 4. And then can you do the 4th root of x squared? No, you don't have enough x's to do a fourth root, so that's going to stay under the fourth root. So just do it like one part at a time. I just did the x's. Now I'm going to do the y's. Same thing. 7 divided by 4 doesn't divide nicely, right? So I'm going to break that up and say, like, what's a multiple of 4 that will divide nicely by the root when I turn it into a rational exponent that's under 7? Y to the 4th. So this can be the 4th root of y to the 4th times y cubed. And then the 4th root of y to the 4th is y. There's like 4 over 4 now. The root is in the denominator. So that's going to be a y to the first. That's on the outside. And then this 4th root of y cubed, I don't have enough y's to 4th root it. So y cubed gets stuck under the 4th root with x squared. This part up here at the top is trying to show that, like, the power on the outside, where it says x to the m divided by n, that's like if you take 6 divided by 4, 4 will go in one time. So it's x to the 1 outside. But then 6 divided by 4, the remainder of that division is 2. So x squared is stuck on the inside. And then 7 divided by 4 I can get in once. So y to the first comes out. 7 divided by 4 leaves me with a remainder of 3, so y cubed is underneath. Okay. You got questions for me? Okay, let's try C, breaking it up. I have really like 4 different things under the radical, right? So I'm just going to do like 4 separate simplifies. I'm going to try the cube root of 24. I'm going to try the cube root of x to the 6th. I'm going to try the cube root of y to the 5th. And I'm going to do the cube root of z squared, if I can. I'm going to do all of those cube roots. Okay, is 24 on your list of perfect cubes? No. Can it be simplified? Are there any factors of 24 that are on your list of perfect cubes? 8. Okay, so this is the cube root of 8 times 3. The cube root of 8 is a nice number of 2. And then this cube root of 3, 3 is not on the list of perfect cubes. I'm going to leave some space to see if I can take out any x, y's, or z's. But I'm going to create a cube root over here, like 3 is stuck there. It's stuck under the cube root. It doesn't come out. So I'm leaving space if I can do any cube roots of the variables, and then I'm leaving space here if any get stuck underneath. Okay. Cube root of x to the 6th is, think about it in rational exponent form. The root is in the denominator. That's x to the 6 over 3, which is x squared. So this one works out nicely, right? No remainder. So it's 2x squared. There's not an x stuck left over. Okay, it divides nicely with no remainder. Let's try this one. Cube root of y to the 5th. Think about it as a fraction exponent. It would be 5 over the root, 3. If you do 5 divided by 3, how many times will 3 go into 5? 3 goes into 5 one time. So we can take a y to the first on the outside. What's the remainder? 5 divided by 3. Remainder 2. So y squared stuck inside. So if you don't, like in the previous ones, I'll write it out here in just a minute. I separated it out into two y's. If you don't want to write that down, you can just think about like how many times does it go in, and then what's my remainder left over. If you did want to write this one out, since it doesn't divide nicely, the first multiple of 3 that divides, that is under 5 is y cubed. So then I have a y squared left over to make y to the 5th. The cube root of y cubed is y. The cube root of y squared remains. And then the cube root of z squared. Think about that as a rational exponent, 2 over 3. You can't even get 2 into 3, right? You don't have enough. So that one's stuck underneath. Nothing gets to come out for the z's. Okay, there's not enough z's to bring one out. There has to be at least 3 of them. Okay. What do you guys think? I feel like I'm losing some people. You got questions for me? Okay, D is just a matter of like, can you subtract those as is? The answer is no. But you should try to simplify both if possible, and then maybe they are actually like terms. So this says 3x times the cube root of x. Well, I can't simplify a cube root of x. That's as low as it would go. This says minus the cube root of 8, which we know is 2. So this is 3x cube root x minus 2. And then the cube root of x to the 4th. Think about x to the 4 divided by 3. How many times does 3 go into 4? Once. So I can bring out an x to the 1st. If you do 4 divided by 3, what's your remainder? 3 goes in once. Remainder is 1. So then we have 1x left over. Are they actually like terms? Yeah. They're both x cube root x terms. I have 3 and I'm subtracting 2 of them. So I have 1 x to the cube root x, or x times cube root x. Okay, those are challenging when you put that simplify mixed in with like adding and subtracting. Because your brain is like, wait, what? So we're going to have tomorrow, if you note over there, it's like a review day. I think we're going to be playing some bingo in class. Okay, so you'll get some chances to like really practice these things. I know it's been a lot coming at you the last 2 days, but that'll be beneficial. I have one last thing real quickly about rationalizing the denominator. We've talked about this before in chapter 2 or chapter 3. And I said we want to work on it because it's going to come back to us. So here it is. You're never allowed to leave a radical in the denominator. So if you have something like cube root of x over 5, break that up. That's the cube root of x over the cube root of 5. You have a radical in the denominator. Okay, so you need to get it out. Normally we just multiply by the square root when we were doing square roots. But if it's a cube root, how many cube roots of 5 do you need? 3 to make 5. How many do we have right there? Just 1 cube root of 5. So I have to multiply it by a cube root of 5 squared times a cube root of 5 squared. A cube root of 5 times a cube root of 5 times a cube root of 5 equals 5. Okay, so it made my denominator the nice number 5, the thing that's underneath the radical, the radicand. And up in the top, I can say this is the cube root of, and I can multiply everything, x times 5 squared. So 25x. Remember, like when I put that square out there, it could be on the 5. I could put parentheses. It's all the same thing. It's the cube root of 5 squared. So it can be the cube root of 25. It's the same. Okay. And then real quickly, the last one, if you want to see cube root of 32 over, or sorry, 5th root of 32 over 5th root of y. You know, the 5th root of 32 is 2. But I can't leave a 5th root of y in the denominator, so I have to multiply by the 5th root of y, but I need 5 of them, so it's got to be to the 4th. The 5th root of y to the 4th. Okay. And my answer there would be 2, 5th root of y to the 4th, all over y. Okay, you do have homework this evening, and like I said, tomorrow we'll quiz each other on our flashcards, we'll go over questions from our homework, and we'll not learn anything new for a day, okay? We'll just get try to do bingo with the properties, so that'll be good for us.
But we like learning 20 formulas.